Pluto, a distant and cryptic heavenly item, was once viewed as an undeniable planet in our nearby planet group. It stood firm on a foothold as a vital individual from our planetary framework until ongoing, momentous proclamations by prestigious astrophysicists Neil deGrasse Tyson and Michio Kaku reignited revenue in Pluto. These recognized researchers have proposed a shocking thought that Pluto may be made a beeline for a horrendous experience with Neptune. Yet, how should such a fantastic situation unfold? And what might the repercussions of such an epic effect at any point be? Are we seeing an exceptional oddity in the universe? Or is there more to this likely enormous occasion than we at first see? Go along with us as we look at the potential results of a theoretical Pluto-Neptune crash. Initially delegated a planet, Pluto was subsequently reimagined as a bantam planet but continues to charm cosmologists and researchers, stirring interest all through the limitlessness of space. Investigations by leading specialists in the field of space science suggest that Pluto's circle perilously brings it near Neptune's orbit. Notable astrophysicists like Tyson and Kaku have raised cautions about the potential dangers presented by a crash between these two divine items, warning that such an occasion could act as a danger to Earth-like worlds. Yet, what might it take for such a devastating event to happen? Pluto's circle around the Sun is strikingly not the same as that of different planets. It requires a surprising 248 years to finish one full revolution, truly meaning that, since its discovery in 1930, Pluto still hasn't completed even a solitary orbit around the Sun. Yet, the interest surrounding Pluto's movement doesn't stop there. Its circle is described by an unusual shape, very dissimilar to the near roundabout orbits of the major planets. Furthermore, Pluto's circle is tilted at a 17 degrees angle compared with the plane of the nearby planet group, making its way substantially more flighty in contrast with other planets. This orbital eccentricity introduces a layer of flightiness with Pluto's movement, convoluting how we might interpret its behavior. A particularly captivating part of Pluto's circle is its interaction with Neptune. During certain times of its orbit, Pluto actually crosses inside Neptune's orbital path, challenging assumptions based on their normal positions inside the planetary group. This brings up a conspicuous issue. Why has Pluto never slammed into Neptune, despite their intersecting orbits? The response lies in the gravitational interactions of other divine bodies inside the planetary group. Following Pluto's discovery, astronomers were initially confused by the curious state of its orbit. Unlike the generally level orbits of most planets, Pluto's path stood out due to its steep tilt and highly irregular shape. This mystery was addressed through a concept called the three-body problem in celestial mechanics, which attempts to understand the movement and interactions of three divine bodies, Pluto, Neptune, and the Sun, all under their shared gravitational influence. This concept is similar to predicting the future positions of these items based on their current locations and the forces acting on them. When applied to Pluto's situation, the three-body problem explains how the Sun, Neptune, and Pluto interact in an exceptionally complicated way. Key terms like libration, oscillatory libration, and VSK wobbling play a significant role in solving this puzzle. Astrophysicists suggest that the general stability of planetary orbits might be credited to a phenomenon called libration. Specifically, when Pluto crosses Neptune's orbit, the relative positioning of the two bodies is balanced by roughly 90 degrees, which plays a critical role in keeping their orbits from aligning and leading to a crash. Libration, which refers to the swinging of an object in its orbit, ensures that Pluto stays well above the plane of the orbits as it approaches Neptune or other massive planets, thus offering protection against potential impacts. Another element maintaining Pluto's orbit is the VSK wobbling, named after the scientists who first studied the movement of objects in space. The VSK wobbling describes how the gravitational forces between Pluto, Neptune, and the Sun affect the movement of each object, ensuring Pluto's orbit remains stable even as it follows an erratic path. This intricate gravitational interaction helps preserve the stability of Pluto's orbit over long periods, despite the apparent chaos of its path. The three-body problem is key to understanding how celestial objects interact, providing insights into Pluto's movement and helping astronomers predict the behavior of distant stars, planets, and other heavenly bodies. Numerical simulations from the late 1980s revealed that, Although Pluto's orbit is extremely irregular, its trajectory remains relatively stable, with only minor deviations from its initial conditions. These steady characteristics of Pluto's orbit have endured over time, allowing astronomers to refine their models of its motion. Recent computational studies have also clarified what large planets, such as Neptune, Jupiter, and Saturn, mean for Pluto's orbit. One unique feature of Neptune's relationship with Pluto is their orbital resonance, a 2-to-3 ratio, where, for each 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance stabilizes Pluto's orbit and prevents a crash. However, Neptune's gravitational influence isn't the only factor at play. Jupiter's massive gravitational pull also plays a significant role in keeping Pluto's orbit stable. Additionally, Saturn's gravity provides further stability to the outer reaches of the solar system. Studies suggest that Jupiter's enormous gravitational field alone is sufficient to maintain the stability of Pluto's orbit for billions of years, possibly ensuring it stays on its current trajectory indefinitely. Together, Neptune, Jupiter, and Saturn work in unison to prevent Pluto's orbit from becoming unstable, contributing to the overall stability of the solar system. Without these forces, the universe would be much more chaotic, with objects like Pluto potentially colliding with other bodies or being ejected from their orbits, causing major disruptions throughout the cosmos. Understanding Pluto's orbital elements is especially significant, particularly as theories about a future collision with Neptune develop. The intricate relationship between Pluto's orbit and Neptune offers valuable insights into how neighboring planetary systems interact. Pluto's case illustrates how even orbits that seem highly erratic can achieve stability due to the complex gravitational interactions at play. Studying Pluto's orbit highlights the need for ongoing observation to ensure that our understanding of the universe remains current. Investigating space often brings us face to face with the odd and unpredictable nature of celestial objects. Pluto's orbit epitomizes this unpredictability, demonstrating that even the most turbulent systems can maintain a steady course due to gravitational forces. The 2:3 orbital resonance between Pluto and Neptune is a critical component of this system, ensuring that, despite their intersecting paths, the two bodies avoid a collision. This gravitational relationship is the foundation of celestial mechanics, showing how even the most irregular orbits can achieve harmony over time. Despite Neptune's influence, other large planets, such as Jupiter, Saturn, and even Uranus, play vital roles in maintaining the balance of the solar system. Jupiter's immense gravitational field acts as a protective force, keeping smaller objects like Pluto on course. Some researchers hypothesize that Jupiter's gravity may have even prevented Pluto from being ejected from the solar system, further emphasizing the importance of these gravitational forces. Understanding the gravitational elements inside our nearby planet group, while Pluto's orbit remains stable for the present, it's vital to recognize that changes could happen in the far-off future. Astrophysicists like Neil deGrasse Tyson continue to explore the universe, uncovering further insights into the forces that govern the movement of celestial bodies. Although the probability of a Pluto-Neptune crash remains low, the very possibility of such an event serves as a reminder of the ever-changing nature of the universe. It highlights the importance of continued investigation to expand our knowledge of the forces shaping our solar system. As the study of Pluto's orbit and its interactions with other celestial objects advances, it remains crucial for advancing our understanding of the broader universe. Pluto's situation serves as a case study for the complexities of orbital resonance, where the movements of celestial bodies are intricately connected. The 2:3 orbital resonance between Pluto and Neptune ensures that, despite their crossing paths, the two bodies never impact. This gravitational equilibrium has protected Pluto's orbit for billions of years, illustrating how forces within seemingly chaotic systems can lead to stable, predictable outcomes. The significance of this resonance cannot be overstated. It reflects a fundamental principle of celestial mechanics, demonstrating that even complex orbital behaviors can achieve harmony through gravitational forces. Understanding orbital resonance goes beyond the relationship between Pluto and Neptune, offering insight into the broader dynamics of the solar system. The interactions between planets, dwarf planets, and other celestial bodies are crucial to maintaining the stability of our planetary system. Jupiter plays a critical role in this process. Its massive gravitational influence acts as a shield for smaller bodies like Pluto, preventing them from veering too far from their established paths. Jupiter's gravity also extends beyond Pluto, affecting the orbits of asteroids, comets, and other small objects in the outer solar system. This interconnectedness underscores the role of gravitational forces in preserving equilibrium within the solar system. Some scientists even speculate that Jupiter's gravitational pull may have helped secure Pluto's position in its current orbit, preventing it from being ejected from the solar system. This further reinforces the idea that each planet plays a specific role in maintaining the solar system's overall structure. Focusing on Pluto's orbit and its gravitational interactions with other planets reveals the dynamic nature of space. While mathematical models and simulations provide valuable insights into celestial mechanics, they also expose the inherent uncertainty of predicting long-term movements. Small changes in initial conditions or minor deviations in gravitational forces can lead to vastly different outcomes over time, highlighting the complexity and unpredictability of space. This uncertainty reinforces the need for continuous observation and analysis. Studying systems like Pluto provides essential lessons about the forces that govern the motion of celestial bodies. Pluto's orbital stability, despite its anomalies, emphasizes the power of gravitational forces and the automatic nature of orbital mechanics. As space exploration advances, it becomes increasingly clear that understanding the delicate balance of these forces is crucial to uncovering the broader dynamics that govern both our solar system and the universe at large. As research into Pluto's orbit and its interactions with other celestial bodies continues, it sheds light on the fundamental principles that govern the solar system's behavior. The fact that Pluto has maintained its orbit for billions of years, despite its seemingly erratic path, highlights the extraordinary nature of gravitational interactions. These interactions help preserve order, even when objects like Pluto appear to follow eccentric trajectories. The importance of maintaining this balance cannot be overstated, as it plays a critical role in preventing catastrophic events within our solar system. Moreover, the ongoing study of Pluto's orbit highlights the complexity of space exploration and the need for constant monitoring. While Pluto's trajectory seems stable today, future changes in gravitational forces could lead to unexpected shifts. Astrophysicists, including Tyson and Kaku, continue to emphasize the interconnectedness of celestial objects and how understanding these connections is vital for predicting the future of our solar system. They argue that even small gravitational disturbances can have significant long-term effects, underscoring the fragile nature of cosmic equilibrium. One of the most intriguing aspects of the ongoing study of Pluto's orbit is how it illustrates gravitational resonance in action. The 2:3 orbital resonance between Pluto and Neptune clearly shows how two objects can share overlapping paths without colliding, thanks to the stabilizing forces at play. Such resonances are not unique to Pluto and Neptune. Similar relationships exist between other planets and their moons, as well as among asteroids and other objects in the solar system. These orbital resonances help prevent chaos by ensuring that celestial bodies remain on their designated paths without interfering with one another. Additionally, Jupiter's role in stabilizing Pluto's orbit cannot be overlooked. With its massive gravitational field, Jupiter acts as a stabilizing force, ensuring that Pluto and other objects stay on their trajectories. Jupiter's influence extends well beyond Pluto, affecting many bodies in the outer solar system. Its role in stabilizing the solar system emphasizes the interconnectedness of these massive celestial objects. Without Jupiter's gravitational influence, Pluto's orbit might have been more vulnerable to disruption, potentially even resulting in its ejection from the solar system. This further reinforces the idea that the solar system operates as a finely tuned system, with each planet and moon playing a specific role in maintaining overall stability. While these gravitational interactions help keep the solar system balanced, they also raise important questions about the long-term evolution of planetary orbits. The fact that Pluto's orbit has remained largely unchanged despite its irregularities speaks to the automatic mechanisms of celestial mechanics. However, this stability is not guaranteed, and even minor changes in the gravitational forces acting on Pluto could alter its path. This possibility underscores the importance of continued observation and modeling to understand the forces shaping the future of the solar system. The ongoing study of space, particularly by researchers like Tyson, provides further insights into the behavior of celestial bodies. Their work refines our understanding of orbital mechanics and helps predict the future movements of planets, moons, and other objects. These predictions are valuable in understanding the dynamics of the solar system and beyond, into the broader universe. By studying objects like Pluto, scientists can learn how gravitational forces govern the movements of celestial bodies over vast periods, revealing the interconnectedness of the universe. Moreover, the potential for changes in Pluto's orbit in the distant future, whether due to shifts in gravitational forces or other unforeseen factors, serves as a reminder of the unpredictable nature of space. Even the most stable systems can undergo changes over time. As we continue to explore the universe, we must remain open to new discoveries and recognize the limitations of our current understanding. In this context, while the possibility of a Pluto-Neptune collision seems distant, it serves as a reminder that vast scenarios can unfold unexpectedly. The likelihood that Pluto's orbit could change after billions of years of stability reflects the ever-evolving nature of the universe. As astrophysicists continue to push the boundaries of our understanding, they highlight how gravitational interactions can both stabilize and potentially disrupt the paths of celestial bodies. The complexity of Pluto's orbit offers a fascinating glimpse into the dynamics of space. By focusing on the interactions between Pluto and Neptune, scientists gain a better understanding of the forces that shape our solar system, as well as other planetary systems throughout the universe. These insights help us appreciate the delicate balance that governs the movement of celestial bodies and the ongoing processes that influence their behavior. They also emphasize the importance of continued research and exploration, as our understanding of space is constantly evolving. In the end, Pluto's orbit, with its intricate interactions with Neptune, Jupiter, and other planets, serves as a perfect example of how gravitational forces shape the solar system. While Pluto's orbit remains stable for now, the ongoing study of its trajectory reveals the complexities and uncertainties that govern the universe. The potential for a future Pluto-Neptune impact, though unlikely, reminds us of the dynamic and ever-changing nature of space. Focusing on Pluto and other celestial bodies expands our understanding of the forces at work in the universe, helping us predict the future behavior of planetary systems and ensuring that our knowledge of the universe continues to grow.